Hello, everybody. Welcome to the Computer Science 46,000 Programming Language offered by Lewis University. My name is Dr. Eric Chow. Welcome to the Chapter 1 Introduction for this course, Programming Languages. Today, we will be discussing the introductory topics for programming languages. Objective: Introduction to Programming Language, programming paradigms, interpretation of computer programs, compilation and interpretation, scripting language versus programming languages. So today, our main focus is introduced to this course, programming language. And this course, programming language, we mainly focus on the programming paradigms, including the imperative programming, object-oriented programming, and also functional programming. And besides these different programming paradigms, we will also be talking about the scripting language and the programming language, the difference between them, and compare and contrast for these two terms. And we will also introduce to you the programming language pragmatics. And these are the interpretation of the computer programs, and it includes compilation and interpretation. So this course is considered to be a course for the structure and the interpretation of computer programs. And we use Python language as the pilot language. Session 1, Introduction to Programming Languages. There's a lot of different languages. We have human language. We also have programming language. These languages are different, and different language used for communication in different situations. So when we talk about programming language, it includes a high-level language, assembly language, and machine language. And the machine language has an interface to the hardware by the instruction set. And usually we call it instruction set architecture. So for example, your machine code may be supported by Intel processor. And the Intel processor may have different clock rate. Maybe some of them has a clock rate of 1 gigahertz. Some of them may have 3 gigahertz. So this processor of different clock speed, they will be compatible because the instruction set is compatible. So machine code and the instruction set provide the compatibility between different processors. And this processor can be of different technology, different semiconductor technology, and also different clocking strategy. And also the memory may be different. And then we have the assembly language, and assembly language is a human readable language, but it has one-to-one mapping to the machine code, almost one-to-one, I should say. Nowadays, there may be some macro or some pseudo instruction being introduced for assembler. But in the old days, there is a one-to-one mapping between your assembly code and machine code. And the assembly language is more readable than machine code. So usually people will teach assembly code for you to understand how the machine works. And then we have the high-level languages such as C++, C language, Java, Python, these different languages that actually can be compiled to the machine code. And sometimes you can actually integrate some program from the high-level language and some from the assembly language using linker to link them together, using linker to link their object code together to create a big executable program so that it can be run on the hardware. So right here, we mainly focus on the high-level language, and the different machine code and assembly language will not be our main focus. We primarily talking about the design of these different high-level languages and also the translation of the high-level language to the machine code, or the translation of the high-level language to the interpreter. And we will get started to talk about these topics. First, I still would like to cover the machine code. And machine code basically is binary code. So it actually has a lot of 0 and 1 for the representation. And usually in your processor, it is a lot of 0-1 combination as your machine code. But 0-1 is very hard to understand. So sometimes they are also being written into the hexadecimal code. And each of the 4 bits, we group them into a half byte. And a half byte is a hexadecimal digit. We can also call it hex digit. And then a byte has 2 hex digits. And you may also have its corresponding ASCII code symbols on the right side. So sometimes you look at the debugger's dump for the memory, it will look like this. So right here, we actually not going to dig too much into the machine code because it's not our main focus, but I just give you a short, brief introduction of what is machine code. Second, we have assembly code. So assembly code has one-to-one mapping to the machine code. So it is some simple instruction. So usually you may have a instruction like push L, okay? L may be a long integer or integer. So, and these are the registers. So here you have push, move, subtract, okay? Call some subroutine. So call some subroutine for get interrupt for reading, okay? So call interrupt, and you will return with some value. So here, these are the instructions, okay? And there are some extra labels for you to handle the program operations. So basically, sometimes you actually may have jump to A, something like that. Or here, jump equal to D, okay? So these are different instructions for the assembly code. Assembly code is more readable, but yet it's not English-like language. So usually it's also being used only by the engineers, hardware engineer. But basically it's a little bit better than machine code. So right here, you can see an example of the assembly code for GCD in the x86 computer instruction set architecture. Okay, we briefly go over the machine code and assembly code just up to that level. We don't dig into any deeper. So right here, you can see the most popular programming language in the year 2021. And we can see that actually there are some desktop programming languages such as C++, and maybe also Java, also Python. These are main desktop languages. And there are some scripting languages such as Perl, okay, PHP, okay. And then there may be some web programming languages such as JavaScript, okay, and some app developer like Xcode, and some framework language like Ruby on the Rail or Swift. Okay, this is actually for apps. Anyway, here just introduce you some basic and popular programming languages. Here, as you can see, it's a tree of the languages, primary tree for the language. So in the old day, we had a first programming, high-level programming language. That is the Fortran language. And Fortran language is short for formula translator. So formula translator. So apparently it's used for the scientific calculation. And then we also have a common business-oriented language, that's COBOL. So that is used for business language. And we also have the old AI language called Lisp language. So basically from day one, the programming language have been used in scientific domain, in business domain, and in functional programming and AI domain. So this feature later developed into Scheme and then developed into Racket language. And also have the ML, okay, these are main functional programming and AI use language and logical programming languages such as Prolog. And then scientific side, we have the Fortran, and then later it developed into Algo, Algorithm 60, Algorithm 68. And then from Algo 60, we developed into C, and C developed into C++. And then that's about the year 1980s. And then 95, Java, okay? And in the 90s, C also developed into Perl and into Python. It's early 90s, we have the Python languages, okay? So that's the so-called scientific calculation. And then COBOL actually is not, it is popular for a long time, but there are not too many dissident language by COBOL. We had the PL1 programming language #1. And later, the whole thing for business being taken over by some website programming languages and also database SQL, SQL, and also framework languages such as Python or this kind of different languages. Okay, so these are the family tree for different programming languages. And why are there so many programming languages? Basically, there is some reason for evolution. So evolution, say here, we can see that language coming from unstructured programming language. We call it structural, we call it sequential programming language. Then we move into the structural programming. And we have Algo 60A, and also Pascal and C language. These are typical structured programming languages. So we start to see the for loop, while loop, okay, the structured programming. And later we develop into object-oriented programming languages. So programming paradigm being introduced for object-oriented programming. And later, this different language also added with functional programming features. And those functional programming features originally coming from Lisp and Scheme, but being added into the mainstream languages. So evolution is one of the reasons why there are so many languages. There are also social economic reasons, such as the company issues. So some vendors support certain languages, such as the Java language is primarily being supported by Oracle and also by the Android system by Google. And in C#, F# is primarily supported by Microsoft. So there's also some socio-economic reasons why some companies just support some languages. Some government projects just use Ada for defense purpose. So these are the so-called socio-economic reasons why different languages have been used. And they are orientation towards special purpose. For example, some language like JavaScript is used primarily for web front-end development. And they are also oriented towards special hardware application, such as Verilog language, that's only for hardware synthesis. Okay, so evolution, you have a long way to go from C, C++, Java, Python, Go, Dart, Swift. So more feature being added into the same family, language families. And we do see a lot of different language keep moving. And social economic reasons, company, for performance, for productivity, for generosity, for generality, and these may be the reason for why there are so many languages. Okay, what makes a language successful? Number one, it must be easy to learn. So basic Pascal logo scheme, these are languages that's pretty easy to learn. For example, I recently reviewed my knowledge on Lisp scheme and bracket, and it just takes me about half an hour to really be able to do programming. So easy to learn is one of the reasons why you need to have a language be designed in a certain way. So to make your language be successful, you must make the language easy to learn. Also, you must make it easy to express your idea. So easy for programmer to become fluent in that language. So C language, Common Lisp, these languages are popular because they are easy to express things. And then also easy to implement. Don't take too much effort to write the compiler. And then possible to compile very good code. Very good code means high performance, small and fast. And also sometimes also related by the sponsors. For example, COBOL by IBM, Visual Basic by Microsoft. Okay, these are also very important factor for a language to be successful. Then wide dissemination of at minimal cost. So basically, these are different factors of making a language successful. Why do we have programming languages? What is a programming language for? So basically, you can program in machine code or assembly, but it's not really that convenient. So it is against our way of thinking. So we like to have a high-level language that's more English-like language, so you can use it to express your ideas in an easiest way. So way of thinking is a reason why we pick a certain language. Number two, the language from user point of view. So not only the grammar need to be more English-like, but also you want it to be a good tool for the programmer to use. So programmers sometimes feel comfortable or efficient to do certain way. We may create a language in that way. And then abstraction of virtual machine, that actually is to specify what you want. And then using a virtual machine, then you don't need to be bound by the hardware, and you can have the language be more platform independent. So the hardware to do without getting down to bits. So you also want to make sure that the programming language can handle whatever idea you have, and you don't need to go down to the tedious work of dealing with number of bits. And some language also is it actually is from implementator's point of view. For example, some people just claim that dynamic linking is better than static linking. So whether your language support dynamic linking or static linking, sometimes it's not a choice of a user, but a choice of the implementators. Okay, next we are on the topic of the programming paradigm. So there are two major groups of the programming paradigms, declarative and the imperative. So imperative is the normal manual machine that has a processor and memory. So those kind of the manual machine is C, Ada function. These are the so-called imperative programming language. Then we have the object-oriented programming language. These are usually being considered as a manual machine language as well. It is a object-oriented programming language on top of the monument machine. And we have Java, C#, and also Smalltalk FL. These are the object-oriented programming language. Then we may also have the scripting language. Scripting languages such as Perl, Python, and PHP. And these different scripting language may be talking to the virtual machine, talking to a interpreter, maybe talking to a browser engine, such as JavaScript, talking to the browser. So usually the scripting language is talking to certain web engine or certain virtual machine or certain processor of a special kind. Then on the declarative side, we have functional programming that's using the paradigm of function calling function. And we have this scheme bracket. This is one programming language family, Haskell and also ML, OCaml. Okay, OCaml is one of the dialect for ML. That's a functional programming using function calling function way. And we have data flow programming language such as IDVol. Data flow language such as IDVol are not really that popular, but some tool like Simulink in MATLAB, they take over the data flow idea. So when you do programming, you put in the input and output boxes, and your data flows through these different boxes. So data flow language usually have input, output, and you flow through different boxes. And then we have logic programming, that's Prolog, spreadsheet, SQL. That's logic based. They use AND OR. They may also use the fact and rule reasoning or logical programming. So imperative, functional, and object-oriented programming, these are the three major paradigms nowadays. And typical imperative programming language is somewhat same like C language. And then object-oriented programming, we have C++ and Java. And also Python also had the object-oriented programming language feature. And then we have functional programming languages such as Python also support functional programming language feature. And also the ML scheme, Lisp. And C++ 20 also support functional programming. So in this course, we use Python as our pilot language. A pilot language means we use it to introduce the different features of this different programming paradigm. We call it a pilot language. We use that. We use Python as our main pilot language to study these different features. So in chapter 1, we have this introduction. Chapter 2, 3, we're talking about data. So data, we have the data model and also the data types system. Chapter 4, we are on the imperative programming. Chapter 5, 6, we are on object-oriented programming. Chapter 7, 8, and 9, we are on functional programming. So basically, the first half of the course is really on these different popular programming paradigms. So functional programming, you have function calling function, that's functional programming. And logic programming, you actually design your program using fact and rule. So right here, we have three facts: John like Jane, and Jane like John, and also Jack like Jane. Three likes relationship. So these are arguments and objects. So John like Jane, okay, and Jane like John is a separate fact. Okay, then there's a rule. Friend rule. Friendship is defined by if there are two people, they are friends, basic X like Y and also Y like X, then it will be a pair of friends. So right here, these are dual and fact. And out of the dual and facts, we also have evaluation Q query. Okay. So we may ask, is friends of John and Jane? So basically, we have the John and Jane, and we evaluate like of the John to Jane, and also like of Jane to John. So we find them both in effect. So then we can make the conclusion that friendship between John and Jane actually exists. On the other hand, if we explore the query of the friendship between Jack and Jane, Jack like Jane, but Jane doesn't like Jack. So there's no friendship between these two people. So programming in this way, we call it logical programming, logic programming, and Prolog is such a language that supports this programming paradigm. Data flow programming. So data flow programming, I picked this one called MATLAB Simulink. Okay, MATLAB language that's more like a scientific programming language, very similar to Python or I should say maybe Fortran. But Simulink is a different language. It actually is on top of MATLAB packages, but you do see the source and sink of each function block. So you open a source folder that will be an image file, and then a file folder, and you would actually see another file, and you can pick one, and you pick one, and you can use the read image, basically use a read image functional block to read the image, and then the data flow to another stage to do smoothing of the image that actually may be a image filter. And then we actually send the output of the smoothed image to a white image processor. Okay, so these are the so-called data flow. Each function block is described by its input and output. So basically, we do programming using this data flow. That's called data flow programming. And the Simulink is a typical language that supports the data flow programming. Von Neumann machine model. John von Neumann is the gentleman who invented such a machine. His main contribution is to put the memory into computer. So putting memory into computer to do storage. In the early day, people don't have such an idea. They only know about using the electronics to design a machine that actually can solve logical problem. So Mr. Von Neumann's main contribution is to introduce the idea of memory and buffer into our computing system. So nowadays we honor him for his contribution of bringing the memory into the computing world. And I should say nowadays, maybe almost every machine is a Von Neumann machine. Almost everyone, I should say, more than 99% of the CPU are supporting Von Neumann type computing, and the CPU is designed primarily for the C language, like programming languages. Okay, so this is the Von Neumann programming model, that including the logic and also the memory. And the logic portion also can be divided into two more parts. One is the control unit, and that actually translates the instruction into control signals, and also has a arithmetic unit. We call it ALU, arithmetic logic unit, ALU. And then ALU usually we can also call it the data path. So it actually is the stages of the data processing for your computing in your CPU. So basically, the existing processor usually load your program from memory and then load to the CPU, and CPU do the processing. And most of the machine right now actually is supported by the basic imperative programming languages. So it is a model that more suitable for variable locations, and also using agents to get the memory location and load it to CPU, and CPU do calculation. So this one actually is the executing your program by instructions, and instructions are orders. So we call it imperative programming language, that using instruction by instruction by instruction, order by order by order. So that's called imperative programming languages. The next one is the imperative programming language, but we call it object-oriented programming paradigm. So the imperative programming language using the manual machine is statement after statement after statement, instruction after instruction after instruction. Okay, but we can group those instructions or statements into functions, and then also grouping some memory location into the memory models, such as objects. And then these give the birth of the object-oriented programming. And object-oriented programming is a label of abstraction that deal with the objects. And each object has data and method that associate with the object. And objects grouping together may create a template. We call it class. And the class may have a template. Sometimes we call it meta class. Okay, so these are the so-called object-oriented programming. And it is based on the manual machine as well, but it is have higher level of the abstraction compared to the manual machine models. Okay, next one is scripting language. Scripting language usually using the idea of virtual machine. Okay, so right here, your machine code is completely detached from your language. So the virtual machine can be a program that operate on your processor. It can be a web engine. So scripting language just do programming, creating scripts, and that runs on the other program. So we call it scripting languages. But scripting language is also one kind of the imperative programming, because usually it also has instruction after instruction type of program code orders. Okay, so right here we can see there is one C language for GCD, calculation of greatest common denominator. And then we have in the middle the same GCD written in OCaml language, that's functional programming. And we can also see there is another program that written in Prolog to do the same thing for the GCD. Okay, interpretation of computer programs, session 3, interpretation versus compilation. So now we know about the different programming paradigm, and then we also knowing about different programming languages. Now we want to know about how these different languages are interpreted onto machine. So we need to know about the compilation and interpretation. Okay, these terms now are more vague, not like before. In the old day, the compilation and interpretation are totally different things. But nowadays, a lot of programming language are hybrid or even mixed. So compilation and the interpretation right now are, I should say, sometimes intertwined together to provide service for compilation or interpretation. So right here in this course, we use these three examples, Python, Java, and C++, to explain to you the difference between compilation, that's C++, hybrid model, that's front-end compilation, back-end interpretation, that's using the Java virtual machine, that's Java. And then we also talk about pure interpretation-based languages such as Python. Pure compilation. So if your language is pure compilation, that means that you just feed the whole program source code into the compiler, and the compiler will finish the translation and then provide the target code in a single pass in a process. So the compiler translates a high-level language from source code to an equivalent target code, and that's similar to people who actually write an essay, say, for example, in Japanese language, and then there's someone who actually translate for you. So the whole article being translated in one word, okay? That's called compilation. So it is possible to compile C into Java, of course, yes. Compilation between high-level language is also possible. Okay, pure interpreter. Interpretation is a different way to do translation. So usually interpretation means that there's a middleman. Okay, so we have president from two countries. So this guy talked to the translator in A language, and he relayed the idea to the other person in B language. And this guy talked in B language, and then he translated into A language for it. So basically, this is the so-called interpretation. And interpretation means there's a middleman in the middle to help translate doing translation. And Python, actually, when you do programming, you are talking to the Python interpreter all the time. You enter one statement, it gives you some translation. You enter another one, it gives you the translation. So it's more like Q&A based, question and answer, question and answer. And nowadays we have a new term called reprint, re-evaluate, print, and then look back. Okay, so that's also pure interpreter based. Okay, comparison. Interpretation usually give you higher flexibility, better for diagnosis of the error message. But the problem is the interpretation, because it actually is controlled by a virtual machine or a translator. So in terms of performance, it actually is slower. You are talking to a program, not talking to the hardware. And the compilation usually is faster because your source code program being translated into the machine code. So usually the hardware speed is higher than the software speed. So compiled program actually is faster. But sometimes the compiler will give you a whole dump of the error message. So it becomes harder for programmer to understand where it went wrong. So there are pros and cons between interpretation and compilation. And some language actually use the so-called hybrid model. So these languages, such as the Java language, is so-called hybrid model. And commonly, it is actually in the preprocessor using the compilation to translate into some bytecode. And then when the bytecode being loaded to the Java virtual machine, then it will do just-in-time compilation and doing interpretation. So front end, you use compilation, back end use interpretation. We call it hybrid compiler or hybrid model for translation. Okay, Java has the virtual machine, so your source code will be translated into some sort of intermediate code. In Python, in Java's case, we call it bytecode, and the bytecode will be loaded along with your input of the user into the virtual machine, and virtual machine doing just-in-time translation for you and run your code and data to provide the output. This is so-called virtual machine. Because of the introduction of the virtual machine, some language like Java become platform independent. That means the same program can be run on a machine that use the Windows, and it can also run on Android system. It can also run on Macintosh, Mac OS. So it can be cross-platform, even cross-hardware for these different languages with virtual machine. Okay, so Java program being compiled to bytecode, and the same bytecode being sent to different virtual machine on the Mac OS, on the Windows, and on the Linux. And these different platform would have one native virtual machine to do translation from the bytecode to the machine code and run it. So this we call it hybrid model, and hybrid model become much more popular because of its performance is close to compiler, and also because of its nature of being platform independence. You do not need to compile your Python program into your Java program into different machine code. The Java virtual machine will handle it for you. Okay, the next section will be on the interpretation of the computer programs. So compilation strategy. Every language may use one or more of these different compilation strategies. So example will be shown for a certain language, but it may not be the only language that use the strategy. And also one language may use multiple strategy, may not be only one strategy. Okay, a preprocessor. A preprocessor is used by C language and C++ language to remove the comments, white spaces, group characters into tokens, such as keywords, identifier, numbers, and symbols. And sometimes it spends abbreviation in the style of a macro assembler, and identify high-level syntactic structures such as loop and subroutine. And these are the so-called preprocessors. So your source code, maybe my.cpp, will be processed by a preprocessor into the source code. And then you have compiler to compile it to the object code. And the object code with some library code will be linked together by the linker, and then link into one executable. Okay, this is the traditional way of doing compilation. So different preprocessor directive command will perform different tasks. We can categorize the preprocessor directive as follows. So these are the four major type of the directives. Inclusion directives. These are include statements. So you actually use the program from different module would use this include directive. Macro definition directive, so define, undefined. These are macro derivative, and the preprocessor will replace your macro with its definition. And then this one is conditional compilation derivative. This one saying which part you will compile, which part you don't need to compile. And there are some other derivatives such as error, line, and pragma. Pragma sometimes for different module. Okay, these are the preprocessors. And strategy B is the library of routine and linking. Okay, because a lot of program may be pre-programmed by other people, so they may be put into the library. And usually in the old days, these library are .o codes, the object codes, and your source code being compiled to another object code called .o, and these different .o module being linked together by the linker. So in the old day, we have the so-called compile link go process. Compile source code into object code, and then linker using linker to link the .o code into .exe, and then the third stage is go to do execution. So we call it compile link go process in the old day for C++ language. But nowadays, a lot of language, because of the virtual machine, is no longer using this kind of compiling go process. Strategy C, post-compilation assembly. So you can compile the source code into assembly, not really the object code, okay? And then you use assembler to put them together into machine code. So that's called post-compilation assembly. This one is okay. It will facilitate the debugging. Okay, so assembly code easier for people to read the machine code. So in terms of debugging in the old days, some people welcome this type of compilation. And you will also isolate the compiler from changes in format of machine code file. Okay, so only assembler need to be changed. Okay, but nowadays very few people will do this because it is still too low level to many programmers. Okay, strategy D, the C processor, the conditional compilation, C preprocessor. Okay, so you have a source code. You actually using the inline code or some macro that will do expansion. So preprocessor delete portion of code, which allows several versions of program to be built from the same source code. So there are some multiplication will happen in the conditional compilation. Usually, this conditional compilation means the directive. Means the directive you may have if and if not defined, if defined or if not defined, then you can actually choose which part of the code you will compile and which part of the code you don't want to compile. Okay, that's C preprocessor conditional compilation. Sometimes conditional compilation also being used for the different hardware models. Okay, strategy E, source to source translation. So you can do C languages compile to C++ or C++ compile to C language or C to assembly language. So this language translation we call source to source translation. C++ implementation based on the early AT&T compiler generate an intermediate code in C language. Okay, so that's called source to source translation. Again, this one nowadays, very few people will do this. Okay, the interpretation of computer programs. So above, we talk about the so-called compiler strategy. Now we talk about the strategy for interpretation. So the compiler generates the code that make assumption about a decision that won't be finalized until runtime. If these assumptions are valid, the code runs very fast. If not, dynamic checking, which will revert to the interpreter. Okay, so this is the compilation for the interpreted languages. And typically, Python and JavaScript are this type of language. And Python has the bytecode for the Python virtual machine. And JavaScript doesn't have the bytecode. JavaScript basically just being run by the so-called web engine by itself. nowadays there are some people trying to create the binary JavaScript, okay, and that actually is a new idea, but we haven't seen it being popular to too many situations. Strategy G, dynamic and just-in-time compilation. We talk about it for Java. So sometimes late compilation or late interpretation is good. So in some cases, a programming system may deliberately delay the compilation until the last possible moment. And especially for some languages like Java, they do translation from the source code to an intermediate code called bytecode. So bytecode is very similar to a binary code, but it's machine independent. So when you do, you try to run the bytecode, when you want to run the program, then at that time we do just-in-time compilation to compile the bytecode into the so-called machine code. Okay, so by doing this, actually, making your program more portable in different systems. You can send the bytecode to different location to run, and you become machine or platform independent. So C# compiler produced .NET common intermediate language that's called CIL. That's similar to bytecode. Okay, similar to bytecode. Okay, this is the so-called Java just-in-time compiler. So your Java program being compiled to bytecode, and then you can send the bytecode for different people to use. And sometimes we do see the jar file, the Java archive file. Okay, you can send the jar file to different location. So jar files is a little bit similar to the .exe file. The only difference is that .exe file really is machine dependent or native code for the machine. And jar file is intermediate code, basically purely in bytecode format. But machine code still be faster. Sometimes this the so-called bytecode and using just-in-time compilation still take a little bit longer. Okay, a little bit longer. But nowadays, because the machine already be so fast, so only some very critical work that you really need to use a native code. Otherwise, just-in-time compilation is almost as good as the machine code now. So in Java development kit, we have Java jar debugging tool, okay, and we have Java runtime environment, Java, okay, library, and then we also have Java virtual machine that's a just-in-time compiler. This is the environment for Java language. Okay, strategy H, we have the microcode instruction translated to microcodes. This actually is the operation of your processor may be coded into microcode, and then your instruction is will be translated into microcode because before it being executed by the control unit. Okay, so these are another level of the translation. We call it microcode programming. Okay, programming environment. So we have Macintosh machine, we have Linux machine, we have Windows machine. They will have different type of the tool for code development. So right here, I'm talking about the Unix system or Linux system. The example is not important because you may use different things. But remember, the editor is for your source code editing. Pretty printer that actually create more prettier printing format. Preprocessor that actually expand your code or reducing your code. Debugger that help you to find the bugs. Styling checker that will make your code more style or follow some coding standard. Module management and version management. These are the integration of your software, version control, and also module control. And then assembler that actually is responsible to translate your assembly language to the machine code. And then link editor is a linker or loader. Okay, so these are used in the compiling Go software or programming languages. Perusal tools and the program cross-reference. These are some other tools. Okay, next one, source code editor. We have Notepad++. And in our course example, I use Notepad++ and also use Visual Studio Code. Nowadays, Visual Studio Code become more popular. It is a lightweight editor, but it's cross-language. Okay, so I prefer Visual Studio Code now. And it's supported by Microsoft, so the tool is very robust. Okay, but in the old day, people do use the integrated environment, IDE, integrated development environment. So we have Eclipse that almost support every language. Netbeans also almost every language. So these are different language IDE. Nowadays, I would say that Eclipse still very popular. Visual Studio Code is popular. IntelliJ IDEA is popular, and Anaconda is also very popular for AI and data science, and Android Studio. Okay, these are different IDE being popular or used in different languages. Okay, Maker is the old days integration tool to make your compile and build your binary code. And we also have VCS. Okay, nowadays people may use GitHub to git your program to provide a version control. But in the old day, we do need to check in into version control software and check out for editing, and then check in when it is done. That's version control. So this one is GitHub Pro, the newer way to do it. You commit change, pull requests, and test changes, and then create branch merge, create branch merge, create branch merge. This is the so-called GitHub development flow. Okay, compilation, the analysis of a computer program structure. Here we have 6 phases for compilation stages. The first stage is called lexical analysis. Second stage is syntax analysis. Third stage is semantic analysis and code generation. And fourth stage is actually code generation, but it is machine independent generation. So we can call it the intermediate code. Okay, we can call it as the intermediate code. We can call it as an intermediate code, or sometimes bytecode is done over here. So compiler may finish at this stage. And after that, we will actually do target code generation and code optimization. Okay, that's called so-called backend. So before the intermediate code or bytecode, we call it front end. And when it's machine dependent, we call it backend. So first stage is scanning, we call it lexical analysis, but divide the program into tokens. And tokens are the smallest meaningful unit. So we usually compare token to the English words. Okay. And word is actually built by the letters. But each letter doesn't have its own meaning. So only words has meaning. So words are minimum meaningful unit. But because we want to make sense for our machine, we do need to translate it into tokens. Okay, so we load a file and then we break it down into tokens, and each token representing one meaningful word in the machine. Okay, and we can tune the scanner better if its job is simple. It also saves complexity for later stages. You can design parser take character instead of the tokens as input, but it's not pretty. Okay, so usually scanner stage is using regular language or DFA, deterministic finite automata. We'll talk about this later, but just remember the main purpose of the first stage is to break down your program into tokens, which is the smallest meaningful unit. Then we had a DFA translation, okay? Translate your letters into the tokens. We'll talk about this later, okay? Second stage is parsing. Parsing is based on your token flow. We pass it into context-free structure of the program. So basically, we will build a syntax tree based on your tokens, okay? And that we call it parsing. Build from your token string into the syntax tree, we call it parsing. So we also call this one parsing as syntax analysis. And syntax analysis will require push-down automata because you need the state, because you may need to call some function or jump to certain location. So there's a call and return procedure. We call it we need this kind of the push-down automata. Okay, the third stage is called semantic analysis. So after you obtain the so-called syntax tree, you may need to evaluate it. Then we call it semantic analysis. For example, you assign a character to a string that may not be acceptable. So it is okay that you put those things into a syntax tree, but it doesn't make sense. And the making sense part, we call it the semantic analysis. And this means that it can be figured out at the compile time of some problem that you see, okay? So that's semantic analysis. But semantic analysis has the static analysis that is run by the compile time. And they are also dynamic semantics at the runtime. Okay, next one, from semantic analysis, we have the code generation, generated into intermediate format. And this portion, we say it is machine independent. So usually we just compile it into some sort of intermediate form, or nowadays, more popular term is the so-called bytecode, okay? Okay, the last two stages are targeted for the intermediate code to the so-called target machine code. And this, we actually do code generation, and then based on the register allocation and also branching condition, we do optimization. So code generation and optimization, we call it back-end design for the compiler. Okay, along with the compilation stages, we will need to have symbol table. Symbol table, we usually keep track of each identifier, such as available function name, into the symbol table, and we may need to call them, use them, or refer them. So the machine table is existing for every stages of the compiler. Okay, compilation analysis of computer program structures. So front end, we have the so-called lexical analysis, parser, semantic analysis, okay? And it will create bytecode or intermediate code. So right here, we have a GCD program in C language. Is written down in this way. And we have this source code. And it will be tokenized using the scanner in two tokens. So basically right here, you can see int is a token, main is a token, parenthesis is a token, right side parenthesis is another token, left side brackets is token. So here we have a token be breaking down into different tokens. Okay, so that's source code is this, and it being break down into tokens. And then after that, we use the content-free grammar to verify it and build the so-called syntax tree. So based on the grammar, and we build the code, GCD code into the parsing tree or syntax tree like this. So it's so huge. We don't go into the detail, but remember this is the structure of your program when it's being compiled using a parser to build into the syntax tree. And based on the syntax tree, we do build such a syntax tree and later for evaluation and generate the intermediate code. So the design of compiler and interpreter. So basically, we get the bunch of characters, we do tokenization, put them into a bunch of words, and then we build them into a syntax tree, and then we do something at the back end. So here, same thing, we use the expression and being tokenized into IDs. And then we actually build a syntax tree, and then we generate the assembly code. This code generation can be assembly code or binary code for executable for the machine code. It can also be run directly by the virtual machine. So the later stage can be, there are many different options. Okay, so here we show you a compiler structure that takes the program input. And we also use the lexical rule to create the so-called scanner. I see this parser and scanner actually are messed up. Scanner should be on the left side. So this one actually is scanner. Sorry for that. I may use the wrong slice. I may copy from the wrong source. The guy makes a mistake. So these two are actually should be swapped. Okay. And then we may have a content-free grammar to generate the scanner. So your program goes through scanner and then parser and then create the result. Okay, this one actually has bugs. So basically, we use the so-called calculators dual EX put into the Python. Python is parser, okay, and you generate the so-called derivative to your flex, and flex with your RTL, your regular expression will generate your the scanner, okay, and you also create your the so-called table, okay, you also create your table, symbol table. And this is just two putting together to generate a compiler. So we create a compiler for the calculator language in this way. And that one can accept the calculator language input and generate the executable code or assembly or interpreter. Okay. So here is another one. This one doesn't use the compiler, doesn't use the interpreter. It is the so-called read, evaluate, print, and then loop back, okay, format. So take the expression to the reader and then build a parsing tree and then do evaluation and then provide the result. So there are key repeat parts. Actually, it's a program structure representation, parsing, tokenization, environment function, evaluation, and repeat. Okay, repeat loop. These are key parts. So right here, I should say the compiler technology nowadays have been breaking down into several possible options. One is the compiler approach. One is the interpreter approach. Another one is actually build in your compiler or translation into the replay format. So in this course, we will discuss all three possible routes of doing interpretation of your program. So these are key terms we may see later in chapter 15 or 16. This is the end of the chapter 1, and thank you for watching this video. Let me know if there is any question. Thank you. Bye now.